Learning objectives. In this chapter, the user would learn the following in detail: axioms and probability, Bayes formula, expectations of random variables, jointly distributed random variables, conditional expectation, bivariate and multivariate Gaussian distribution, some applications, a list model, a random graph. Limit theorems, random number generation, simulating continuous random variables, Monte Carlo integration, information theory, measure of uncertainty, Shannon's measure, entropy, joint and conditional entropies, mutual information, Goldberg-Leibler, directed divergence, coding theory and entropy. Bayes theorem statement: if E1, E2, etc. En are mutually disjoint events with P of Ei not equal to 0 where I equal to 1, 2, etc. n, then for any arbitrary event A which is a subset of union I equal to 1 to n Ei such that P of A greater than 0, we have P of Ei given A equal to P of Ei into P of A given Ei divided by summation I equal to 1 to n P of Ei into P of A given Ei where I equal to 1 to etc. n. Proof: since Ei is a subset of union I equal to 1 to n Ei, we have A equal to A intersection union I equal to 1 to n Ei equal to union I equal to 1 to n A intersection Ei. Since A intersection Ei is a subset of Ei or mutually disjoint events, we have P of A equal to P of union I equal to 1 to n A intersection Ei equal to summation I equal to 1 to n P of A intersection Ei equal to summation I equal to 1 to n P of Ei into P of A given Ei. Also we have P of A intersection Ei equal to P of A into P of Ei given A. Therefore, P of Ei given A equal to P of A intersection Ei divided by P of A equal to P of Ei into P of A given Ei divided by summation I equal to 1 to n P of Ei into P of A given Ei. Example: the contents of urns 1, 2 and 3 are as follows: 2 white, 3 black and 4 red balls, 3 white, 2 black and 2 red balls, and 4 white, 1 black and 3 red balls. An urn is chosen at random and 2 balls are drawn. They happen to be white and red. What is the probability that they come from urns 1, 2 and 3? Let E1, E2 and E3 denote the events that the urn 1, 2, 3 be chosen respectively, and let A be the event that the 2 balls taken from the selected urn be white and red. P of E1 equal to P of E2 equal to P of E3 equal to 1 by 3. Therefore, P of A given E1 equal to 2C1 into 4C1 divided by 9C2 equal to 2 by 9. P of A given E2 equal to 3C1 into 2C1 divided by 7C2 equal to 2 by 7. And P of A given E3 equal to 4C1 into 3C1 divided by 8C2 equal to 3 by 7. Now we want to calculate P of E1 given A, P of E2 given A and P of E3 given A. Therefore, P of E1 given A equal to P of E1 into P of A given E1 divided by summation I equal to 1 to 3 P of Ei into P of A given Ei equal to 1 by 3 into 2 by 9 divided by 1 by 3 into 2 by 9 plus 1 by 3 into 2 by 7 plus 1 by 3 into 3 by 7 equal to 0.23787. P of E2 given A equal to P of E2 into P of A given E2 divided by summation I equal to 1 to 3 P of Ei into P of A given A equal to 1 by 3 into 2 by 7 divided by 1 by 3 into 2 by 9 plus 1 by 3 into 2 by 7 plus 1 by 3 into 3 by 7 equal to 0.30509. Then P of E3 given A equal to 1 minus 0.23727 plus 0.30509 equal to 0.45764. Example: in a bolt factory machine, A, B, C manufactures respectively 25, 35 and 40% of the total of their output, 5, 4 and 2% are defective bolts respectively, what are the probabilities that it was manufactured by machines A, B or C? Given that P of A equal to 25 by 100 equal to 0.25, P of B equal to 35 by 100 equal to 0.35, P of C equal to 40 by 100 equal to 0.40. Let D be the event which denotes the defective bolt. From the data we have P of D given A equal to 5 by 100 equal to 0.05, P of D given B equal to 4 by 100 equal to 0.04, P of D given C equal to 2 by 100 equal to 0.02. The probability that the bolt is defective from the product is P of D equal to P of A into P of D given A plus P of B into P of D given B plus P of C into P of D given C equal to 0.25 into 0.05 plus 0.35 into 0.04 plus 0.40 into 0.02 equal to 0.0345. The probability that the defective bolt is manufactured by A is P of A given D equal to P of A into P of D given A divided by P of D equal to 0.25 into 0.05 divided by 0.0345 equal to 0.36232. Similarly, P of B given D equal to 0.35 into 0.04 divided by 0.0345 equal to 0.40579. Then P of C given D equal to 0.40 into 0.02 divided by 0.0345 equal to 0.23188. Coding theory. Coding theory is one of the most important and direct applications of information theory. It can be subdivided into source coding theory and channel coding theory. Using a statistical description for data, information theory quantifies the number of bits needed to describe the data, which is the information entropy of the source. Data compression, source coding. There are two formulations for the compression problem. Number 1, lossless data compression. The data must be reconstructed exactly. Number 2, lossy data compression. Allocates bits needed to reconstruct the data within a specified fidelity level measured by a distortion function. The subset of information theory is called rate distortion theory. Error correcting codes, channel coding. While data compression removes as much redundancy as possible, an error correcting code adds just the right kind of redundancy, that is, error correction needed to transmit the data efficiently and faithfully across a noisy channel. This division of coding theory into compression and transmission is justified by the information transmission theorems or source channel separation theorems that justify the use of bits as the universal currency for information in many contexts. However, these theorems only hold in the situation where one transmitting user wishes to communicate to one receiver user. In scenarios with more than one transmitter, the multiple ACES channel, more than one receiver, the broadcast channel, or intermediary helpers, the relay channel, or more general networks, compression followed by transmission may no longer be optimal. Network information theory refers to these multi-agent communication models. Entropy. Entropy of an information source. Based on the probability mass function of each source symbol to be communicated, the Shannon entropy H in units of bit per symbol is given by H equal to minus summation I pi into log base 2 pi, where pi is the probability of occurrence of the ith possible value of the source symbol. This equation gives the entropy in the units of bits per symbol because it uses a logarithm of base 2, and this base 2 measure of entropy has sometimes been called the Shannon in his honor. Entropy is also commonly computed using the natural logarithm base e, where e is the Euler's numbers. which produces a measurement of entropy in nats per symbol and sometimes simplifies the analysis by avoiding the need to include extra constants in the formulas. Other bases are also possible but less commonly used. For example, a logarithm of base 2 power 8 equal to 256 will produce a measurement in bytes per symbol, and a logarithm of base 10 will produce a measurement in decimal digits or Hartleys per symbol. Intuitively, the entropy Hx of a discrete random variable x is a measure of the amount of uncertainty associated with the value of x when only its distribution is known. The entropy of a source that emits a sequence of n symbols that are independent and identically distributed IID is nh bits per message of n symbols. If the source data symbols are identically distributed but not independent, the entropy of a message of length n will be less than n minus h. The entropy of a Bernoulli trial as a function of success probability, often called the binary entropy function, HB of p. The entropy is maximized at 1 bit per trial when the two possible outcomes are equally probable, as in an unbiased coin toss. Suppose one transmits 1000 bits, zeros and ones. If the value of each of these bits is known to the receiver as a specific value with certainty ahead of transmission, it is clear that no information is transmitted. If, however, each bit is independently equally likely to be 0 or 1, 1000 shannons of information, more often called bits, have been transmitted between these two extremes. Information can be quantified as follows. If x is the set of all messages x1, x2, etc. xn that x could be, and p of x is the probability of x belongs to capital X, then the entropy h of x is defined h of x equal to ex of I of x, that is equal to minus summation x belongs to capital X p of x into log p of x. Here I of x is the shelf information, which is the entropy contribution of an individual message, and ex is the expected value. A property of entropy is that it is maximized when all the messages in the message space are equiprobable. P of x equal to 1 by n, that is most unpredictable, in which case h of x equal to log n. The special case of information entropy for a random variable with two outcomes is the binary entropy function, usually taken to the logarithmic base 2, thus having the Shannon h's as unit. HB of p equal to minus p log base 2p minus of 1 minus p log base 2 of 1 minus p. Joint entropy. The joint entropy of two discrete random variables x and y is merely the entropy of their pairing x, y. This implies that if x and y are independent, then the joint entropy is the sum of their individual entropies. For example, if x, y represents the position of a chess piece, x the row and y the column, then the joint entropy of the row of the piece and the column of the piece will be the entropy of the position of the piece. H of x, y equal to E of x, y minus log P of x, y equal to minus summation x, y P of x, y into log P of x, y. Despite similar notation, joint entropy should not be confused with cross entropy. Conditional entropy, equivocation. The conditional entropy or conditional uncertainty of x given random variable y, also called the equivocation of x about y, is the average conditional entropy over y. H of capital X given capital Y equal to E capital Y of H of capital X given small y equal to minus summation small y belongs to capital Y P of small y into summation small x belongs to capital X P of small x given small y into log P of small x given small y equal to minus summation small x comma small y P of small x comma small y into log of P of small x comma small y divided by P of y. Because entropy can be conditioned on a random variable or on that random variable being a certain value, care should be taken not to confuse these two definitions of conditional entropy, the former of which is in more common use. A basic property of this form of conditional entropy is that h of capital X given y equal to h of capital X comma capital Y minus h of capital Y. Goldberger-Leibler divergence. The Goldberg-Leibler divergence or information divergence, information gain, or relative entropy is a way of comparing two distributions, a true probability distribution P of X and an arbitrary probability distribution Q of X. If we compress data in a manner that assumes Q of X is the distribution underlying some data, when in reality P of X is the correct distribution, the Goldberg-Leibler divergence is the number of average additional bits per datum necessary for compression. It is thus defined DKL of P of X given Q of X, we using a capital X, equal to summation small x belongs to capital X minus P of small x into log Q of small x minus summation small x belongs to capital X minus P of small x into log P of small x equal to summation small x belongs to capital X P of small x into log P of small x by Q of small x. Although it is sometimes used as a distance metric, KL divergence is not a true metric since it is not symmetric and does not satisfy the triangle inequality, making it a semi-quasi-metric. Another interpretation of the KL divergence is the unnecessary surprise introduced by a prior from the truth. Suppose a number capital X is about to be drawn randomly from a discrete set with the probability distribution P of X. If Alice knows the true distribution P of X while Bob believes as a prior that the distribution is Q of X, then Bob will be more surprised than Alice. An average upon seeing the value of capital X. The KL divergence is the objective expected value of Bob's subjective surprisal minus Alice's surprisal measured in bits if the log is in base 2. In this way, the extent to which Bob's prior is wrong can be quantified in terms of how unnecessarily surprised it is expected to make him. Definition. Let X be a random variable with the possible values x1, x2, etc. xn and then etc. Let P of xi equal to P of x equal to x, that means capital X equal to small xi, where I equal to 1, 2, etc. Then the expected value of x denoted by E of x, that is called expectation of x, is defined as E of x equal to summation I equal to 1 to infinity xi into P of xi. If the series E of x equal to summation I equal to 1 to infinity xi into P of xi converges absolutely if x is a continuous random variable with PDF, that is probability density function, then U of x equal to integral minus infinity to infinity x into f of x dx if this integral is absolutely convergent. Example. Suppose a random variable x takes the values 0 factorial, 1 factorial, 2 factorial, etc. with the probabilities P of capital X equal to small x equal to e power minus 1 divided by xi factorial. Then E of x equal to 0 factorial into e power minus 1 by 0 factorial plus 1 factorial into e power minus 1 by 1 factorial plus etc. equal to e power minus 1 into 1 plus etc. till infinity, which is divergent. Therefore, E of x does not exist. Example. A Cauchy distribution was defined by the PDF. F of x equal to 1 by pi into 1 plus x square for minus infinity less than x less than infinity. Then U of x equal to integral minus infinity to plus infinity x into f of x dx equal to integral minus infinity to plus infinity x into, we just want to substitute our f of x here. That means 1 by pi into 1 plus x square into dx. Then after integrating, we get 1 by 2 pi log of 1 plus x square with the limits minus infinity to plus infinity, which does not exist. Then E of x does not exist for Cauchy distribution. Definition. Let x be a random variable and y equal to h of x if y is a discrete random variable with possible values y1, y2, etc. and q of y1, q of y2, etc. and their probabilities, the expectation of y is defined as E of y equal to summation I equal to 1 to infinity yi q of yi, provided the series on right hand side is absolutely convergent. If y is a continuous random variable with PDF q of y, then we define E of y equal to integral minus infinity to plus infinity y into q of y into dy if it exists. Important results. Let x be a random variable and y equal to h of x. If x is a discrete with probability function p of xi, then E of y equal to summation j equal to 1 to infinity h of xi into p of xi. Then if x is a continuous random variable with PDF f of x, then E of y equal to integral minus infinity to plus infinity h of x into f of x into dx. Example. A random variable x is a probability function as follows. The problem with two rows. First row is called the values of x, second row is called the probability values. In the first row, we having minus 1, 0 and then 1. The second row, we having the values 0.2 is the value of minus 1, 0.3 is the value of 0, 0.5 is the value of 1. Evaluate. Subdivision 1, expectation of 3x plus 1. Subdivision 2, expectation of x square. Solution for subdivision 1. Expectation of 3x plus 1 equal to summation 3x plus 1 into p of x. Then equal to minus 3 plus 1 into 0.2 plus 0 plus 1 into 0.3 plus 3 plus 1 into 0.5. After solving this, we getting the value 1.9. We know that expectation of 3x plus 1 equal to 3 into expectation of x plus 1. Subdivision 2, E of x square equal to summation x square into p of x equal to 1 into 0.2 plus 0 into 0.3 plus 1 into 0.5. After solving this, we getting 0.7. In some places, we using expectation of x and then E of x. Don't get confused. We can use expectation of x or E of x. Both are same only. Definition. Let x comma y be a two-dimensional random variable and z equal to h of x comma y be a real valued function of x comma y. Then x is a one-dimensional random variable and expectation of z is defined as follows. Subdivision 1. If z is a discrete random variable with possible values z1, z2, etc. and p of zi equal to zi, that means capital Z equal to small zi, then expectation of z equal to summation I equal to 1 to infinity zi into p of zi if the series on the right hand side is absolutely convergent. Subdivision 2. If z is a continuous random variable with PDF f of z, then E of z equal to integral minus infinity to plus infinity z into f of z into dz if the integral is absolutely convergent. Result. Let x comma y be a two-dimensional random variable and z equal to h of x comma y if x comma y is a discrete random variable with the probability function p of xi comma yi, then E of z equal to summation j again summation I h of xi comma yi into p of xi comma yi if it exists. If x comma y be a continuous random variable with joint probability density function f of x comma y, then expectation of z equal to integral minus infinity to infinity again integral minus infinity to plus infinity h of x comma y into f of x comma y into dx into dy if it exists. Important results. If c is a constant, then expectation of c equal to c. Then if c is a constant and y equal to h of x is a random variable then expectation of c into h of x equal to c into expectation of h of x. If x is a random variable and g1 of x and g2 of x are functions of x, then expectation of g1 of x plus g2 of x equal to expectation of g1 of x plus expectation of g2 of x, assuming that the expectations of g1 of x and g2 of x exist. Then expectation of g1 of x less than or equal to expectation of g2 of x if g1 of x less than or equal to g2 of x for all x. Then modulus of expectation of g of x less than or equal to expectation of modulus of g of x. If x comma y is a two-dimensional random variable defined on a sample space S, then expectation of the sum is equal to the sum of the expectation. Expectation of x plus y equal to expectation of x plus expectation of y. Let x1, x2, etc. up to xn be n random variables defined on a sample space S. Then expectation of x1 plus x2 plus etc. plus xn equal to expectation of x1 plus expectation of x2 plus etc. plus expectation xn. Then expectation of ax plus b equal to a into expectation of x plus b, where a and b are constants. Then expectation of summation I equal to 1 to n ai into xi equal to summation I equal to 1 to n ai into expectation of xi. If x and y are independent random variables defined on a sample space S, then expectation of xy equal to expectation of x into expectation of y. Let x1, x2, etc. till xn be n random variables defined on a sample space S, then expectation of x1, x2, etc. till xn equal to expectation of x1 into expectation of x2, etc. expectation of xn. Example: show that the expected number of failures preceding the first success in a series of Bernoullian trials with a constant probability of success p is 1 minus p by p. Solution: define the random variable x as the number of failures preceding the first success. Then the possible values of x are 0, 1, 2, 3, etc. Now we put in the tabular column with two rows. One is values of x, another one is called p of x. P of x is called the probability values. The values of x are 0, 1, 2, 3, etc. Then the probability values are p is the value of 0, and then pq is the value of 1, pq square is the value of 2, pq cube is the value of 3. Then expectation of x equal to 0 into p plus 1 into pq plus 2 into pq square plus 3 into pq cube plus etc. equal to, after taking the pq as common, we writing inside the bracket 1 plus 2q plus 3q square plus etc. Then equal to pq into 1 minus q whole power minus 2. Then again equal to pq divided by 1 minus q the whole square equal to p into 1 minus p divided by p square. Again equal to 1 minus p divided by p. Example: find the mean of x when x is defined by f of x equal to 0 for x less than 0, x for 0 less than or equal to x less than 1, 3 minus x divided by 4 for 1 less than or equal to x less than 3, then 0 otherwise. Expectation of x equal to integral minus infinity to plus infinity x into f of x dx equal to integral 0 to 1 x square into dx plus integral 1 to 3 x into 3 minus x divided by 4 into dx equal to x cube by 3 integral 0 to 1 plus 3x square by 8 minus x cube by 12 with the limit 1 to 3 equal to 1 by 3 plus 27 by 8 minus 27 by 12 minus 3 by 8 minus 1 by 12 equal to 7 by 6. Variance definition: let x be a random variable, then the variance of x is denoted by variance of x or sigma x square is defined by expectation of e minus e of x whole square. That means x minus expectation of x whole square. The positive root of variance is called standard deviation of x and is denoted by sigma x. Formula for variance of x. Variance of x equal to expectation of x square minus expectation of x whole square. If c is a constant, then variance of x plus c equal to variance of x. If c is a constant, variance of c into x equal to c square into variance of x. Then variance of ax plus b equal to a square into variance of x. If x comma y is a two-dimensional random variable and if x and y are independent, variance of x plus y equal to variance of x plus variance of y. Let x1, x2 up to xn be n independent random variables, then variance of x1 plus x2 plus etc. plus xn equal to variance of x1 plus variance of x2 plus etc. plus variance of xn. Then expectation of x minus c the whole square is a minimum when c equal to expectation of x. Example. Find the mean and variance of the probability function p of x equal to e power minus 2 power x divided by x factorial, where x equal to 1, 2, 3, etc. 0 otherwise. Solution. Expectation of x equal to summation x into p of x equal to summation 1 equal to 1 to infinity x into e power minus 2 into 2 power x by x factorial equal to e power minus 2 into summation 1 equal to 1 to infinity 2 power x by x minus 1 factorial equal to 2 into e power minus 2 summation 1 equal to 1 to infinity 2 power x minus 1 by x minus 1 factorial. Again equal to 2 into e power minus 2 into e power 2. Then finally the answer is 2. Expectation of x square equal to summation x square into p of x equal to summation 1 equal to 1 to infinity. We can write the x square like x into x minus 1 plus x into e power minus 2 power x by x factorial equal to summation 1 equal to 1 to infinity x into x minus 1 into e power minus 2 into 2 power x by x factorial plus summation 1 to infinity x into e power minus 2 into 2 power x by x factorial. Then equal to e power minus 2 summation 2 to infinity 2 power x by x minus 2 plus 2 factorial. We have to notice one thing very carefully. One step before, we have used summation 1 to infinity in the first step. Now we are using summation 2 to infinity equal to e power minus 2 into 4 into e power 2 plus 2. Then equal to we getting 4 plus 2. Then the final answer is 6 for expectation of x square. Then variance of x equal to expectation of x square minus expectation of x whole square equal to 6 minus 4 equal to 2. Therefore, mean equal to 2, variance equal to 2. Example. A continuous random variable x as a PDF that is called probability density function given by f of x equal to k into x into e power minus lambda x, x greater than or equal to 0, lambda greater than or equal to 0, then 0 otherwise. Determine the constant k, obtain the mean and variance of x. Solution. F of x equal to k into x into e power minus lambda x, x greater than or equal to 0, lambda greater than or equal to 0, then 0 otherwise. Since f of x is a PDF that is called probability density function, integral minus infinity to plus infinity, f of x dx equal to 1. We substituting the f of x value here, integral 0 to infinity, k into x into e power minus lambda x into dx equal to 1. After integrating this, we getting k into x into e power minus lambda x by minus lambda limit 0 to infinity plus integral 0 to infinity k by lambda into e power minus lambda x into dx equal to 1. Here we are using the UDV formula, uv minus integral v du. After applying the limits, k into x into e power minus lambda x by minus lambda limit 0 to infinity equal to 1, then put k by lambda square equal to 1. Then expectation of x equal to integral 0 to infinity lambda square into x square into e power minus lambda x into dx, then equal to lambda square into, inside the bracket, x square into e power minus lambda x by minus lambda minus 2x into e power minus lambda x by lambda square plus 2 into e power minus lambda x by minus lambda cube, limit 0 to infinity, equal to lambda square into 2 by lambda cube equal to 2 by lambda. Then expectation of x square equal to integral minus infinity to infinity lambda square into x cube into e power minus lambda x into dx equal to, we're just keeping the lambda square outside and then applying the Bernoulli formula. The Bernoulli formula is uv minus u dash v1 plus u double dash v2 minus u triple dash v3 plus etc. Here u is x cube and then v is e power minus lambda x by minus lambda equal to lambda square into, inside the bracket, x cube into e power minus lambda by minus lambda minus 3x square into e power minus lambda x by lambda square plus 6x into e power minus lambda x by minus lambda cube minus 6 into e power minus lambda x by lambda power 4 limit 0 to infinity equal to lambda square into 6 by lambda power 4. After simplifying and then cancelling, we getting 6 by lambda square. Variance of x equal to expectation of x square minus expectation of x whole square equal to 6 by lambda square minus 2 by lambda the whole square equal to 6 by lambda square minus 4 by lambda square. After subtracting, we getting 2 by lambda square. Measures of uncertainty. In metrology, measurement uncertainty is a non-negative parameter characterizing the dispersion of the values attributed to a measured quantity. All measurements are subject to uncertainty and a measurement result is complete only when it is accompanied by a statement of the associated uncertainty. By international agreement, this uncertainty has a probabilistic basis and reflects incomplete knowledge of the quantity value. The measurement uncertainty is often taken as the standard deviation of a state of knowledge probability distribution over the possible values that could be attributed to a measured quantity. Relative uncertainty is the measurement uncertainty related to the magnitude of a particular single choice for the value for the measured quantity when this choice is non-zero. This particular single choice is usually called the measured value, which may be optional in some well-defined sense. Example, a mean, median or mode. Thus, the relative measurement uncertainty is the measurement uncertainty divided by the absolute value of the measured value when the measured value is not zero. Mutual information. Mutual information measures the amount of information that can be obtained about one random variable by observing another. It is important in communication where it can be used to maximize the amount of information shared between sent and received signals. The mutual information of capital X relative to capital Y is given by I of capital X, capital Y equal to E capital X, capital Y inside the bracket S I of small x, small y equal to summation small x, small y p of small x, small y into log of p of small x, small y divided by p of x into p of y, where SI means specific mutual information is the point-wise mutual information. A basic property of the mutual information is that I of capital X, capital Y equal to h of capital X minus h of capital X given capital Y. That is, knowing Y, we can save an average of I of x, y bits in encoding capital X compared to not knowing capital Y. Mutual information is symmetric. I of capital X, capital Y equal to I of capital X, capital Y equal to I of capital Y, capital X equal to h of capital X plus h of capital Y minus h of capital X, y. Mutual information can be expressed as the average Kullbacher-Leibler divergence information gain between the posterior probability distribution of X given the value of capital Y and the prior distribution on X. I of capital X comma capital Y equal to EP of small y into DKL law of P of capital X given capital Y equal to small y given P of capital X. In other words, this is a measure of how much on the average the probability distribution on X will change if you are given the value of capital Y. This is often recalculated as the divergence from the product of the marginal distributions to the actual joint distribution. I of capital X comma capital Y equal to DKL P of capital X comma capital Y given P of capital X into P of capital Y. Mutual information is closely related to the log likelihood ratio test in the context of contingency tables and the multinomial distribution to the Pearson's X-squared test. Mutual information can be considered a statistic for assessing independence between a pair of variables and as a well-specified asymptotic distribution. Learning objectives. In this chapter, the user would learn the following in detail: axioms and probability, Bayes formula, expectations of random variables, jointly distributed random variables, conditional expectation, bivariate and multivariate Gaussian distribution, some applications, a list model, a random graph, limit theorems, random number generation, simulating continuous random variables, Monte Carlo integration, information theory, measure of uncertainty, Shannon's measure, entropy, joint and conditional entropies, mutual information, Goldberg-Leibler, directed divergence, coding theory and entropy. Probability. Theory of probability. In mathematics or statistics, a numerical measure of uncertainty is practiced by the important branch of statistics called the theory of probability. Consider the following day-to-day life statements. Number 1. Every day the sun rises in the east. Number 2. It is possible to live without water. Number 3. Probably Arun gets the job. Look at the above statements. There is certainty in the first, impossibility in the second, and uncertainty in the third statement. In the theory of probability, we represent certainty by 1, impossibility by 0, and uncertainty by a positive fraction which lies between 0 and 1. Importance of probability. It has been developed to a great extent. There is no area in social, physical, or natural sciences where the probability theory is not used. Number 1. It is the base of the fundamental laws of statistics, that is, law of statistical regularity and the law of inertia of large numbers. Number 2. It is an essential tool in statistical inference and forms the basis of the decision theory. Number 3. It gives solution to betting of games. It is now possible to decide whether it is worthwhile betting at a game. Number 4. Different lists of significance are derived by using the theory of probability. Random experiment or trial and event or cases. If an experiment is repeated under the same conditions any number of times, it does not give unique results but may result in any one of the several possible outcomes. Thus, an action or an operation which can produce any result or outcome is called a random experiment or a trial, and the outcomes are known as events or cases. Number 1. Rolling of a die is a trial and getting 6 is an event. Number 2. Tossing a coin is a trial and getting head or tail is an event. Number 3. Drawing a ball from an urn containing black and white balls is a trial and getting a black or a white ball is an event. Sample space. The totality of all possible outcomes of a random experiment is called a sample space S, and a possible outcome or element in a sample space S is called a sample point. Equally likely events. The outcomes are said to be equally likely if one of them is expected to occur in preference to other. Thus, 2 or more events are said to be equally likely if each one of them has an equal chance of happening. For example, when a coin is thrown, the head is as likely to turn up as the tail. Hence, head comma tail, that means h comma t, are equally likely events. Mutually exclusive events are incompatible events. Two events are said to be mutually exclusive when both cannot happen simultaneously in a single trial. If a coin is tossed, either head can be up or tail can be up, but both cannot be up at the same time. Thus, in tossing of a coin, the events head and tail are mutually exclusive events. Similarly, in rolling of a die, occurrence of phases numbered 1, 2, 3, 4, 5 and 6 are mutually exclusive. Exhaustive events. Outcomes are said to be exhaustive when they include all possible outcomes. For example, while rolling a die, the possible outcomes are 1, 2, 3, 4, 5 and 6, and hence the exhaustive number of cases 6. Independent events. Two or more events are considered to be independent if the occurrence of an event does not affect the other. For example, if a coin is thrown twice, the result of second throw is no way affected by the result of the first throw. Thus, the events are independent events. Dependent events. Two events are said to be dependent if the occurrence or non-occurrence of an event in any trial affects the occurrence of other event in other trials. Consider the event of drawing a card twice out of 52 cards without replacement. In the first case, we draw one card out of 52 cards, and the second case, without replacement, we draw one card out of 51 cards only. Thus, the outcome of the first event affects the outcome of the second event, and hence they are dependent. But if the card is replaced before the drawing of the second card, then the total cards remains the same as 52. In that case, events are independent. Complementary events. A is called complementary event of B and vice versa if A and B are mutually exclusive and exhaustive. When a die is thrown, occurrence of an even number 2, 4, 6 and an odd number 1, 3, 5 are complementary events. Definition of probability. It is a mathematical definition of probability. If there are n equally likely, mutually exclusive and exhaustive outcomes and m of them are favorable to an event A, the probability of the happening of A is defined as the ratio m by n. If we denote the probability or chance of the happening of an event A by P, then P of A equal to m by n equal to number of favorable cases divided by total number of exhaustive cases. Note, clearly from the definition of probability, it is a numerical measure and it is a positive number not greater than unity, that is 0 less than or equal to P less than or equal to 1. Let P of A bar or Q be the probability of the event A bar, that is A not happening. The number of cases in which the event A will not happen is n minus m. Therefore, P of A bar equal to Q equal to n minus m divided by n. After dividing by n, we getting 1 minus m divided by n equal to 1 minus P, because P is called m by n. Then equal to, we getting 1 minus P of A. Then, that is, P of A plus P of A bar equal to 1. That is, P plus Q equal to 1. Note, number 1. If P of A equal to 1, the event A is called a certain event, and if P of A equal to 0, the event A is called an impossible event. Also, P of A bar equal to 1 minus P of A. Number 2. The number of favorable events can either be counted or enumerated with the help of permutation and combination. Number 3. The above mathematical definition of probability fails to answer if 1. The events are not equally likely, and 2. The exhaustive number of cases in a trial is infinite. Number 4. Probability of the impossible event is 0, that is, P of empty set equal to 0. We can also call P of phi equal to 0. Example. An integer is chosen from 2 to 15. What is the probability that it is prime? Since there are 14 numbers from 2 to 15, the total number of numbers is 14. Out of 14 numbers, 2, 3, 5, 7, 11, 13 are prime numbers. Hence, the number of favorable numbers is 6. Hence, the probability that the number chosen is prime, P equal to number of favorable numbers divided by total numbers, equal to 6 by 14 equal to 3 by 7. Example, 2 dice are thrown together. Find the probability that we get a total of 9. Here, total number of outcomes equal to 6 square equal to 36. Total number 9 will come if we consider the outcomes 3, 6, 4, 5, 5, 4 and 6, 3. There are 4 favorable cases. Hence, the required probability equal to 4 by 36 equal to 1 by 9. Example, 4 cards are drawn at random from a well-shuffled pack of cards. Find the probability that subdivision 1, all the 4 are queens. Subdivision 2, there is 1 card from each suit. Subdivision 3, 2 cards are diamonds and 2 are spades. Subdivision 1, let A1 be the event that all the 4 cards drawn are queen. There are only 4 queen cards and 4 cards can be drawn in 4C4 ways. Therefore, P of A1 equal to 4C4 divided by 52C4 equal to 1 divided by 2,70,725 equal to 0.000037. Subdivision 2. Let A2 be the event that there is 1 card from each suit. A pack contains 13 cards in each suit. 1 card can be drawn from each in 13C1 ways. Therefore, P of A2 equal to 13C1 into 13C1 into 13C1 into 13C1 divided by 52C4 equal to 0.10549. Third subdivision. Let A3 be the event that 2 drawn are diamonds and 2 are spades. Out of 13 diamond cards, 2 diamond cards can be chosen in 13C2 ways, and out of 13 spades, 2 cards can be chosen in 13C2 ways. Hence, the number of favorable cases for the event A3 equal to 13C2 into 13C2. Therefore, P of A3 equal to 13C2 into 13C2 divided by 52C4 equal to 0.02247. Axioms of Probability. Let S be the sample space, sigma be the class of events, P be a real valued function defined on sigma. Then P is called a probability measure and P of A is called the probability of the event A if P satisfies the following axioms. First subdivision. For every event A belongs to sigma, 0 less than or equal to P of A less than or equal to 1. Subdivision 2. P of S equal to 1. Subdivision 3. For every finite or infinite sequence of disjoint events A1, A2, etc., then P of A1 union A2 union etc. equal to P of A1 plus P of A2 etc. That is, the another way of representing P of A1 union A2 union etc. is called P of union AN equal to summation P of AN. Laws of probability. Addition law of probability. Case 1. When events are mutually exclusive, if A and B are mutually exclusive events, that is, if A intersection B equal to empty, then P of A union B equal to P of A plus P of B, or P of A or B equal to P of A plus P of B. We can represent the union as OR, that is called OR. Case 2. When events are mutually exclusive, if A and B are any two events, then P of A union B equal to P of A plus P of B minus P of A intersection B, or P of A or B equal to P of A plus P of B minus P of A and B. Case 2. If A and B are any two events, subsets of sample space S and are not disjoint, then proof. We have A union B equal to A union A bar intersection B. Since A and A bar intersection B are disjoint, P of A union B equal to P of A plus P of A bar intersection B equal to P of A plus P of A bar intersection B plus P of A intersection B minus P of A intersection B equal to P of A plus P of A bar intersection B union A intersection B minus P of A intersection B equal to P of A plus P of B minus P of A intersection B. Since A bar intersection B and A intersection B are disjoint. Note, if A and B are mutually exclusive, A intersection B equal to empty, that means null set, then P of A union B equal to P of A plus P of B. Subdivision 2. We can generalize the addition law for n events. For n events A1, A2, etc. An, we have P of union I equal to 1 to n, Ai equal to summation I equal to 1 to n, P of Ai minus summation 1 less than or equal to I, again summation less than j less than or equal to n, P of Ai intersection Aj plus summation, again summation, again summation 1 less than or equal to I less than j less than k less than or equal to n, P of Ai intersection Aj intersection Ak plus etc. plus minus 1 whole power n minus 1, P of A1 intersection A2 intersection etc. An. Multiplication law of probability. Case 1. When events are independent, the probability that both independent events A and B will occur is equal to product of the probabilities of each event. Then P of A intersection B equal to P of A into P of B, or P of A and B equal to P of A into P of B. Case 2. When events are dependent, conditional probability. Earlier we have discussed that if the occurrence of an event A is affected by the occurrence of the another event B, then the events A and B are dependent. The probability of event B depending on the occurrence of event A is called conditional probability, and we denote it as P of B given A, and read as the probability of A given B. The probability that both the dependent events A and B will occur is given by P of A intersection B equal to P of A into P of B given A equal to P of B into P of A given B. Theorem: multiplication law of probability, or theorem of compound probabilities. For two events A and B, P of A intersection B equal to P of A into P of B given A, where P of A greater than 0 equal to P of B into P of A given B, where P of B greater than 0, where P of B given A represents the conditional probability of occurrence of B when the event A has already happened, and P of A given B is the conditional probability of happening of A given that B has already happened. Proof: we have P of A equal to n of A by n of S, P of B equal to n of B by n of S, and P of A intersection B equal to n of A intersection B divided by n of S is called equation number 1. For the conditional event A given B, the favorable outcomes must be one of the sample points of B, that is, for the event A given B, the sample space is B, and out of the n of B of sample points, n of A intersection B pertain to the occurrence of the event A. Hence, and P of A given B equal to n of A intersection B divided by n of B. Rewriting equation 1 as P of A intersection B equal to n of B by n of S into n of A intersection B divided by n of B equal to P of B into P of A given B. Similarly, we can prove P of A intersection B equal to n of A divided by n of S into n of A intersection B divided by n of A equal to P of A into P of B given A. Example: the probability that a company director will travel by train is 1 by 5 and by plane is 2 by 3. What is the probability of his traveling by train or plane? Let A be the event for traveling by train or plane equal to P of A or P of B equal to P of A plus P of B. Since A and B are mutually exclusive, equal to 1 by 5 plus 2 by 3 equal to 13 by 15. Example: if we draw a card from a well-shuffled pack of 52 cards, what is the probability that the card is either an ace or a king? The events that the card drawn is either an ace or a king are mutually exclusive. Let the event of the ace drawn be denoted by A1 and the events of king drawn be denoted by A2. A pack has 4 aces and 4 kings. Thus P of A1 equal to 4 by 52 and P of A2 equal to 4 by 52. The probability that the card is either ace or a king equal to P of A1 or A2 equal to P of A1 union A2 equal to P of A1 plus P of A2 equal to 4 by 52 plus 4 by 52 equal to 2 by 13. Example: if A, B, C are mutually independent events, prove that A union B and C are also independent. We have A union B intersection C equal to A intersection C union B intersection C is called distributive law. P of A union B intersection C equal to P of A intersection C union B intersection C equal to P of A intersection C plus P of B intersection C minus P of A intersection B intersection C equal to P of A into P of C plus P of B into P of C minus P of A into P of B into P of C equal to P of C into P of A plus P of B minus P of A into P of B equal to P of C into P of A plus P of B minus P of A intersection B equal to P of C into P of A union B. This implies A union B and C are independent. Quantities of information. Information theory is based on probability theory and statistics. Information theory often concerns itself with measures of information of the distribution associated with random variables. Important quantities of information are entropy, a measure of information in a single random variable, and mutual information, a measure of information in common between two random variables. The former quantity is a property of the probability distribution of a random variable and gives a limit on the rate at which data generated by independent samples with the given distribution can be reliably compressed. The latter is a property of the joint distribution of two random variables and is the maximum rate of reliable communication across a noisy channel in the limit of long block length when the channel statistics are determined by the joint distribution. The choice of logarithmic base in the following formulae determines the unit of information entropy that is used. A common unit of information is the bit based on the binary logarithm. Other units include the NAT, which is based on natural logarithm, and the Hartley, which is based on the common logarithm. In what follows, an expression of the form P log P is considered by convention to be equal to 0 whenever P equal to 0. This is justified because limit P tends to 0 plus P log P equal to 0 for any logarithmic base. Random graph models. A random graph is obtained by starting with a set of n isolated vertices and adding successive edges between them at random. The aim of the study in this field is to determine at what stage a particular property of the graph is likely to arise. Different random graph models produce different probability distributions on graphs. Most commonly studied is the one proposed by Edgar Gilbert, denoted by G of n, P, in which every possible edge occurs independently with probability 0 less than p less than 1. The probability of obtaining any one particular random graph with m edges is p power m into 1 minus p whole power n minus m, with the notation n equal to nc2. A closely related model, the Erdos-Renyi model, denoted by G of n, m, assigns equal probability to all graphs with exactly m edges with 0 less than or equal to m less than or equal to n, G of n, m has ncm elements and every element occurs with probability 1 divided by ncm. The later model can be viewed as a snapshot at a particular time m of the random graph process Gn. which is a stochastic process that starts with n vertices and no edges, and at each step adds one new edge chosen uniformly from the set of missing edges. If instead we start with an infinite set of vertices and again let every possible edge occur independently with the probability 0 less than p less than 1, then we get an object G called an infinite random graph, except in the trivial cases when p is 0 or 1, such a G almost surely has the following property. Given any n plus m elements a1 etc. an, b1 etc. bm belongs to V, there is a vertex C in V that is adjacent to each of a1 etc. an and is not adjacent to any of b1 etc. bm. It turns out that if the vertex set is countable, then there is, up to isomorphism, only a single graph with this property, namely the Rado graph. Thus, any countably infinite random graph is almost surely the Rado graph, which for this reason is sometimes called simply the random graph. However, the analogous result is not true for uncountable graphs, of which there are many non-isomorphic graphs satisfying the above property. Another model which generalizes Gilbert's random graph model is the random dot product model. A random dot product graph associates with each vertex a real vector. The probability of an edge uv between any vertices u and v is some function of the dot product u dot v of the respective vectors. The network probability matrix models random graphs through edge probabilities, which represent the probability pi, j that an given edge ei, j exists for a specified time period. This model is extensible to directed and undirected, weighted and unweighted, and a static or dynamic graphs structure. For m approximately equal to p into n, where n is the maximal number of edges possible, the two most widely used models, g of n, m and g of n, p, are almost interchangeable. Random regular graphs form a special case with the properties that may differ from random graphs in general. Once we have a model of random graphs, every function on graphs become a random variable. The study of this model is to determine if, or at least estimate the probability that a property may occur. Properties of random graphs. The theory of random graphs studied typical properties of random graphs, those that hold with the high probability for graphs drawn from a particular distribution. For example, we might ask for a given value of n and p, what the probability is that g of n, p is connected. In studying such questions, researchers often concentrate on the asymptotic behavior of random graphs, the values that various probabilities converge to as n grows very large. Percolation theory characterizes the connectedness of random graphs, especially infinitely large ones. Percolation is related to the robustness of the graph, also called network, given a random graph of n nodes and an average degree k. Next, we remove randomly a fraction 1 minus p of nodes and leave only a fraction p. There exists a critical percolation that's old Pc equal to 1 by k, below which the network becomes fragmented, while above Pc a giant connected component exists. Localized percolation refers to removing a node, its neighbors, next nearest neighbors, etc. Until a fraction of 1 minus p of nodes from the network is removed. It was shown that for random graph with the Poisson distribution of degree, p underscore c equal to 1 divided by k, exactly as the random removal. For other types of degree distributions, p underscore c for localized attack is different from random attack. Random graphs are widely used in the probabilistic method, where one tries to prove the existence of graphs with certain properties. The existence of a property on a random graph can often imply, via the Zimmerdi regularity lemma, the existence of that property on almost all graphs. In random regular graphs, g of n, r, that means regular, or the set of R regular graphs with R equal to R of n such that n and m are the natural numbers, comma 3 less than or equal to r less than n, and m equal to 2m is even. The degree sequence of a graph G in G power n depends only on the number of edges in the sets. Vn power 2 equal to, inside the flower bracket, I, j, where 1 less than or equal to j, less than or equal to n, comma I not equal to j, is a subset of v power 2, I equal to 1, etc. n. If edges m in a random graph Gm is large enough to ensure that almost every Gm has minimum degree at least 1, then almost every Gm is connected, and if n is even, and almost every Gm has a perfect matching, in particular the moment that the last isolated vertex vanishes in almost every random graph, the graph becomes connected. Almost every graph processes on an even number of vertices with the edge rising the minimum degree to 1, or a random graph with slightly more than n by 4 log n edges and with the probability close to 1 ensures that the graph has a complete matching with the exception of at most one vertex. For some constant c, almost every labeled graph with n vertices and at least cn log of n edges is Hamiltonian with the probability tending to 1. The particular edge that increases the minimum degree to 2 makes the graph Hamiltonian. Coloring of random graphs. Given a random graph G of order n with the vertex v of g equal to 1 to etc. n, by the greedy algorithm on the number of colors, the vertices can be colored with colors 1 to etc. Vertex 1 is colored 1, vertex 2 is colored 1 if it is not adjacent to vertex 1, otherwise it is colored 2, etc. The number of proper colorings of random graphs. Given a number of Q colors called its chromatic polynomial remains unknown so far. The scaling of zeros of the chromatic polynomial of random graphs with parameters n and the number of edges m or the connection probability p has been studied empirically using an algorithm based on symbolic pattern matching. Random trees. A random tree is a tree or arborescence that is formed by a stochastic process in a large range of random graphs of order n and size m of n. The distribution of the number of tree components of order k is asymptotically Poisson. Types of random trees include uniform spanning tree, random minimal spanning tree, random binary tree, tree, rapidly exploring random tree, Brownian tree, and a random forest. Conditionally uniform random graph. Conditionally uniform random graphs assign equal probability to all the graphs having a specified properties. They can be seen as a generalization of the Erdos-Renyi model G of n, m, when the conditioning information is not necessarily the number of edges m but whatever other arbitrary network property. In this case, very few analytical results are available, and a simulation is required to obtain empirical distributions of average properties. Recently, a general and exact methodology for random graph simulation has been proposed by Stefano Nazzini and Joe Di Castro. Interdependent graphs. In interdependent graph, nodes in one network graph depend on other networks to function. So, failures in one or several graphs induce cascading failures between the graphs which may lead to abrupt collapse. Random variables. Let E be an experiment and S is a sample space associated with the experiment. A function x assigned to each element small s belongs to capital S. A real number x is called a random variable. Discrete random variable. A random variable is said to be discrete if it assumes only a finite or countably infinite values of x. That is, a range space capital R contains a finite or countably infinite points. Definition. Let x1, x2, etc. be possible values of a discrete random variable x. then P of xi is called the probability function of the discrete random variable x if subdivision 1 P of xi greater than or equal to 0 for all I equal to 1, 2, etc. Subdivision 2 summation I P of xi equal to 1 continuous random variable. A random variable is said to be continuous if it can assume all points on the real line. Let us now define the probability density function of a continuous random variable. Definition: a function f is said to be the probability density function (PDF) of a continuous random variable x if the following conditions are satisfied. Subdivision 1 f of x greater than or equal to 0 for all x. Subdivision 2 integral minus infinity to infinity f of x dx equal to 1. We have to notice it clearly here. If our problem occurs with summation, that is called discrete. If our problem comes with integration, that is called continuous. Cumulative distribution function. Let x be a random variable, may be discrete or continuous. Then the function f of x is defined by f of x equal to p of capital X less than x is called the cumulative distribution function of x. If x is a discrete random variable, then f of x equal to summation xi less than x p of xi. If x is a continuous random variable, then f of x equal to integral minus infinity to x f of x dx. Every density function f of x satisfies the condition f of infinity equal to integral minus infinity to plus infinity f of x dx equal to 1 and f of minus infinity equal to 0. Also, for every real a and b where a less than b, probability of a less than or equal to x less than or equal to b equal to f of b minus f of a equal to integral a to b f of x dx. Also, if the function f of x is continuous at some point x, then f dash of x equal to f of x. We have to notice it clearly. After differentiating the capital F of x, we will get the small f of x. That's what we written here. Capital F dash of x equal to small f of x. Properties of distribution function. Number 1. F of minus infinity equal to 0 and f of infinity equal to 1. Number 2. F of x is non-decreasing function. That means it's an increasing function. Number 3. F of x is continuous from the left. Number 4. If x is continuous random variable with PDF, that means our probability density function f of x, then f dash of x equal to small f of x. A random variable x has a following probability function. Now we see the problem with the two rows, x and then p of x. X has the values 0, 1, 2, 3, 4, 5, 6, 7. Then p of x has the values. That means probability of x has the values 0, k, 2k, again 2k, 3k, k square, 2k square, and then 7k square plus k. Subdivision 1. Find k. Subdivision 2. Evaluate. Subdivision A. P of x less than 6. Subdivision B. P of x greater than or equal to 6. Subdivision 3. P of 0 less than x less than 5. Subdivision 3. If P of x less than or equal to k greater than 1 by 2, then find the minimum value of k. Subdivision 4. Determine the distribution function of x. Solution. Subdivision 1. Since P of x is a probability function, then summation x equal to 0 to 7, P of x equal to 1. The meaning for this is called, we have to add whatever having in our problem, that means in second row. After adding all the values of P of x, 0 plus k plus 2k plus 2k plus 3k plus k square plus 2k square plus 7k square plus k equal to 1, we get 10k square plus 9k minus 1 equal to 0. After simplifying this, we getting k equal to 1 by 10 or k equal to minus 1. K equal to minus 1 is inadmissible. Then k equal to 1 by 10. From the subdivision 2, we seeing the solution for subdivision A. P of x less than 6 equal to P of x equal to 0 plus P of x equal to 1 plus P of x equal to 2 plus P of x equal to 3 plus P of x equal to 4 plus P of x equal to 5. Then we just want to add all the probability values. 0 plus k plus 2k plus 2k plus 3k plus k square. We getting k square plus 8k. Then the final value is 1 by 100 plus 8 by 10 equal to 81 by 100. Subdivision B. Probability of x greater than or equal to 6 equal to p of x equal to 6 plus p of x equal to 7 equal to 2k square plus 7k square plus k. After adding, we getting 9k square plus k. After substituting the value of k square, we getting 9 by 100 plus 1 by 10 equal to 19 by 100. Subdivision C. Probability of 0 less than x less than 5 equal to x equal to p of x equal to 1 plus p of x equal to 2 plus p of x equal to 3 plus p of x equal to 4 equal to, we just want to add all the probability values here. K plus 2k plus 2k plus 3k equal to 8k. After substituting the value of k, we getting 8 by 10. After simplifying this, we getting 4 by 5. The minimum value of k for this result is true if k equal to 5. This is seen from the following distribution. The table has two rows. X, capital F of x. First row, that means x has the values 0, 1, 2, 3, 4, 5, 6, 7 and then greater than or equal to 7. Now we can see the capital F of x values. 0 stands for 0 and then 0 stands for 1. 1 by 10 for 2, 3 by 10 for 3, 5 by 10 for 4, 8 by 10 for 5, 81 by 100 for 6, 83 by 100 for 7, 1 for greater than or equal to 7. Example. A continuous random variable x is the following PDF means that is called probability density function. F of x equal to 3x square for 0 less than x less than 1. Then 0 otherwise. Verify that it is a PDF and evaluate the following probabilities. Subdivision 1. Probability of x less than or equal to 1 by 3. Subdivision 2. Probability of 1 by 3 less than or equal to x less than or equal to 1 by 2. Third subdivision. Probability of x less than or equal to 1 by 2 given 1 by 3 less than or equal to x less than or equal to 2 by 3. Solution. F of x greater than or equal to 0 for all x. Also, integral minus infinity to plus infinity. F of x dx equal to 1. Integral 0 to 1. 3x square dx equal to. We just want to integrate this function. If we integrate 3x cube divided by 3. We just want to apply the limits here. Limit is called upper limit minus lower limit. Here, integral 0 to 1. 3x square dx equal to. After integrating this, we will get 3x square divided by 3. Limit 0 to 1. After substituting the limit, we will get 1. Therefore, f of x dx is a PDF. Subdivision 1. P of x less than or equal to 1 by 3 equal to integral 0 to 1 by 3. 3x square dx. After integrating this, we will get 3x cube by 3. After cancelling 3 by 3, we simply get x cube and then we want to apply the limit 0 to 1 by 3. After applying the limit, we getting 1 by 9. Subdivision 2. Probability of 1 by 3 less than or equal to x less than or equal to 1 by 2 equal to integral 1 by 3 to 1 by 2 3x square dx. If we integrating, we know we will get x cube with the limits 1 by 3 to 1 by 2. After applying the limits, we will get 1 by 8 minus 1 by 27 equal to 19 by 216. Subdivision 3. Probability of x less than or equal to 1 by 2 given 1 by 3 less than or equal to x less than or equal to 2 by 3. Here we are using the conditional probability. P of A given B equal to P of A and B divided by P of B. Using the conditional probability, we are getting probability of 1 by 3 less than or equal to x less than or equal to 1 by 2 divided by probability of 1 by 3 less than or equal to x less than or equal to 2 by 3 equal to integral 1 by 3 to 1 by 2 3x square dx divided by integral 1 by 3 to 2 by 3 3x square dx. After integrating this, we know very well we will get x cube only. We just want to apply here the limits. For the numerator, we have to apply 1 by 3 to 1 by 2. For the denominator, we have to apply 1 by 3 to 2 by 3. Then 1 by 8 minus 1 by 27 divided by 8 by 27 minus 1 by 27. After simplifying, we getting 9 divided by 8 into 27 into 27 by 7 equal to 9 by 56. Definition. Let x comma y be a two-dimensional discrete random variable. Let p of xi comma yj be a real number associated with each xi comma yj, where I comma j equal to 1, 2, 3, etc. Then p is called the jointly probability function of x comma y if the following conditions are satisfied. Subdivision 1. P of xi comma yj greater than or equal to 0 for all I comma j equal to 1, 2. Subdivision 2. Summation I equal to 1 to infinity. Summation j equal to 1 to infinity. P of xi comma yj equal to 1. Definition. Let x comma y be a two-dimensional continuous random variable. Then f of x comma y is called the probability density function of x comma y if the following conditions are satisfied. Subdivision 1. If x comma y greater than or equal to 0 for all x comma y. Subdivision 2. Integral minus infinity to plus infinity. Again integral minus infinity to plus infinity. F of x comma y dx dy equal to 1. Definition. If x comma y is a two-dimensional discrete random variable with joint probability function p of xi comma yj, then the marginal distribution of x is defined by p of xi equal to summation j p of xi comma yj, and the marginal distribution of y is defined by q of yj equal to summation j p of xi comma yj. Definition. If x comma y is a two-dimensional continuous random variable with the probability density function f, then the marginal distribution of x is defined by g of x equal to integral minus infinity to infinity f of x comma y dy, and the marginal distribution of y is defined by h of y equal to integral minus infinity to infinity f of x comma y dx. Result. Probability of a less than or equal to x less than or equal to b equal to probability of a less than or equal to x less than or equal to b, comma, minus infinity less than y less than infinity equal to integral a to b, again integral minus infinity plus infinity f of x comma y dy into dx equal to integral a to b g of x dx. Similarly, p of c less than or equal to y less than or equal to d equal to integral a to d h of y dy. Conditional probability distribution. Definition. Let x comma y be a two-dimensional discrete random variable with the joint probability function p of xi comma yj. Let p of xi and q of yj be the marginal probability functions of x and y respectively. Then the conditional distribution of y on x is defined by p of xi given yj equal to p of x equal to xi given y equal to yj equal to p of xi comma yj divided by q of yj if q of yj greater than 0. Independent random variables. Definition. Let x comma y be a two-dimensional discrete random variable with the probability function p of xi comma yj. Let p of xi and q of yj be the marginal probability functions of the random variables x and y respectively. Then the random variables x and y are said to be independent if p of xi comma yj equal to p of xi into q of yj. Definition. Let x comma y be a two-dimensional continuous random variable with probability density function f of x comma y. Let g of x and h of y be the marginal probability density functions of the random variables x and y respectively. Then the random variables x and y are said to be independent if f of x comma y equal to g of x into h of y. Example. For the joint distribution f of x comma y equal to 9 by 4 minus x minus y, comma 0 less than or equal to x less than or equal to 2, comma 0 less than or equal to y less than or equal to 2, then 0 elsewhere. Obtain the marginal and conditional distributions. Solution. The marginal distribution of x is g of x equal to integral 0 to 2 9 by 4 minus x minus y into dy equal to 9 by 4 into y minus xy minus y squared by 2, limit 0 to 2. We get this through the integration formulas. Then equal to, after substituting the limits, we getting 9 by 2 minus 2x minus 2. After simplifying this, we getting 5 by 2 minus 2x. Therefore, g of x equal to 5 by 2 minus 2x for 0 less than x less than 2, then 0 otherwise. H of y equal to integral 0 to 2, 9 by 4 minus x minus y into dx. After integrating this function, we getting 9 by 2 minus 2y minus 2. Therefore, h of y equal to 5 by 2 minus 2y for 0 less than y less than 2, then 0 otherwise. The conditional distribution of x given y is f of x given y equal to f of x comma y divided by h of y. We are substituting the values equal to 9 by 4 minus x minus y divided by 5 by 2 minus 2y. Then f of x given y equal to 9 minus 4x minus 4y divided by 5 minus 4y for 0 less than or equal to x less than or equal to 2, comma y belongs to 0, comma 2. We getting this by taking the LCM and doing some simplification here. Similarly, f of y given x equal to 9 minus 4x minus 4y divided by 5 minus 4y for 0 less than or equal to y less than or equal to 2, comma x belongs to 0, comma 2. Example: if the distribution of the random variable x comma y is given by f of x comma y equal to 1 by 4 into inside the bracket 1 plus xy into x square minus y square for modulus of x less than or equal to 1, comma modulus of y less than or equal to 1, then 0 otherwise. Show that x and y are not independent. Solution: g of x equal to integral minus 1 plus 1 1 by 4 into 1 plus xy into x square minus y square into dy. We are just substituting the function what is given in the question. Now we want to integrate it separately. Equal to 1 by 4 into inside the bracket. We just keeping the 1 by 4 as common because it's a constant term. Integral minus 1 to 1 into dy plus x cube into integral minus 1 to 1 y dy. Here we keeping the x cube as constant minus y into integral minus 1 to 1 y cube into dy. Here also we keeping the x as constant. Why we keeping like that? Because we integrating with respect to y. Y is not a constant here, but we keeping like that. Y is also a variable. Keep in mind, y is also a variable. It's not a constant. We just keeping like a constant because x and y are random variables here. Yeah, finally substituting the limits, we getting the value 1 by 4 into 2 plus 0 plus 0. Then the final value is 1 by 2. Similarly, h of y equal to 1 by 2. Then g of x into h of y equal to 1 by 4. Thus, f of x comma y not equal to g of x into h of y. Therefore, x and y are not independent. Example: test whether x and y are independent random variables given that f of x comma y equal to 4xy where 0 less than x less than 1, comma 0 less than y less than 1, 0 otherwise. Solution: g of x equal to integral 0 to 1 4xy into dy equal to 4x into y squared by 2, limit 0 to 1. We getting this through the integration. After applying the limit, we getting the 2x. Therefore, g of x equal to 2x. Similarly, h of y equal to integral 0 to 1 4xy into dy. After integrating and applying the limit, we getting 2y. Thus, g of x equal to 2x where 0 less than x less than 1, then 0 otherwise. H of y equal to 2y where 0 less than y less than 1, then 0 otherwise. F of x comma y equal to g of x into h of y. Hence x and y are independent. Simulation. Introduction. The representation of reality in some physical form or in some form of the mathematical equations may be called simulation. That is, simulation is an imitation of reality. Examples of simulation models. Number 1. Testing an aircraft model in a wind tunnel. Number 2. Children cycling park with various signals and crossing to model a traffic system. Number 3. Planetarium. To determine the behavior of a real system in true environment, a number of experiments are performed on simulated models either in the laboratories or in a computer itself. Advantages of simulation: less complicated mathematically, flexible, modified to suit the changing environments of the real situation, can be used for training purposes, may be less expensive in quite a few real-world situations, may be less time consuming in quite a few real-world situations. Limitations of simulation: quantification of the variables may be difficult. Large number of variables make simulation unwieldy and more difficult. Simulation may not yield optimum results. Simulation may not be cheap always. Simulation may not be less time consuming. Cannot rely too much on the results obtained from simulation models sometimes. When to use simulation? Simulation may be especially used when the problem is susceptible to description by a mathematical model, but the analysis of the model is beyond the level of mathematical sophistication of the analyst. The problem is not susceptible to description by a mathematical model. One is satisfied with suboptimal results for decision making. Monte Carlo technique or Monte Carlo simulation. This technique involves a selection of random observations within the simulation model. It is constrained for application involving random numbers to solve deterministic and stochastic problems. The underlying principle of this technique is: Number 1. Replace the actual statistical universe by another universe described by some assumed probability distribution. Number 2. Sample from this theoretical populations by means of random numbers. Generation of random numbers. Random numbers is a number whose probability of occurrence is the same as that of any number in the collection. Number 1. Random numbers may be drawn from a random number table. Number 2. Random number may be obtained using electronic devices. Number 3. One may use pseudo-random numbers in the place of random numbers. Pseudo-random numbers may be generated by some arithmetic operations. The most commonly used one in the congruence method or the residue method, by using the formula Ri plus 1 equal to Ari plus B modulo M, where A, B are constants, or J, Rj plus 1 or the ith and I plus 1th pseudo-random numbers. R0 is called the seed, which, if chosen properly, may yield a large set of pseudo-random numbers. The validation of pseudo-random numbers is very important. A number of tests are available to test the randomness of the sequence. Some tests to ensure the uniformity and independence of random numbers are frequency test or uniformity test, chi-square test, independence test. Even though there is a large number of tests of randomness, a sequence of pseudo-random numbers that passes the frequency test and independence test will be sufficient for most simulation process. The multiplicative congruential generating xi plus 1 equal to xi into a modulo m, with the value of a, m, x0 taken suitably is found to pass both these tests. Steps in simulation. Number 1. Identify the measure of effectiveness. Number 2. Decide the variables which influence the measure of effectiveness. Choose those variables which affects the measure of effectiveness significantly. Number 3. Determine the probability distribution for each variable in previous step and construct the cumulative probability distribution. Number 4. Choose an appropriate set of random numbers. Number 5. Consider each random number as a decimal value of the cumulative probability distribution. Number 6. Use the simulated values so generated into the formula derived from the measure of effectiveness. Number 7. Repeat 5 and 6 until the sample is large enough to arrive at a satisfactory and reliable decision. Uses of simulation. Simulation is used for solving number 1. Inventive problem. Number 2. Queuing problems. Number 3. Training programs, etc. Example. Customers arrive at a milk booth for the required service. Assume that the inter-arrival and service time are constant and given by 1.5 and 4 minutes respectively. Simulate the system by hand computations for 14 minutes. Subdivision 1. What is the waiting time per customer? Subdivision 2. What is the percentage idle time for the facility? Assume that the system starts at t equal to 0. First customer starts getting the service, so its departure time, because t equal to 0 plus 4 equal to 4 minutes. Next arrival occurs at t equal to 0 plus 1.5 equal to 1.5 minutes, which is listed before d1 at t equal to 4. The facility is still busy. Second customer stands in the queue, and the first one said to be considered in the queue. The third arrival event A4 at t equal to 3.0 plus 1.5. This event succeeds D1 at t equal to 4. At this moment, first customer departs, leaving the service facility free. Second customer, who was the first to join the queue, now gets service. The waiting time is calculated as the time period from the moment he joined the queue until his service is started. This process is repeated until the simulated period is completed. The above problem is clearly explained in the table with the time, event, that means arrival or departure, customer number and waiting time. We can see the table row by row and then we can easily understand. For customers who are yet to service after 14 minutes, the waiting times are given by is shown in the table with the two columns. First column is named as customer number. Second column is named as waiting number in minutes. Now we can clearly see the customer numbers in the table and waiting numbers in minutes in the table. From this simulation table, it is clear that subdivision 1, average waiting time for customer equal to 2.5 plus 5 plus 7.5 plus 8 plus 6.5 plus 5 plus 3.5 plus 2 plus 0.5 divided by 10 equal to 4.05 minutes. Subdivision 2. Average waiting time per customer for those whose wait equal to 40.5 divided by 9 equal to 4.5 minutes. Subdivision 3. Percentage idle time of the facility equal to 0%. Example. A sample of 100 arrivals of customers at a retail sales depart is according to the following distribution. From the table, we can clearly see time between arrivals in minutes and frequency. The time as 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, 4.0, 4.5 and then 5.0, and the frequency is 2, 6, 10, 25, 20, 14, 1.0, 7, 4, 2. A study of the time required to service customers by adding up the bills, receiving payments and placing packages yields the following distribution. We can see this also from the table. Time between service in minutes and frequency in another column. Time between service as 0.5, 1.0, 1.5, 2.0, 2.5, 3.0 and the frequency as 12, 21, 36, 19, 7, 5. Estimate the average percentage customer waiting time and average percentage idle time of the server by simulation for the 10 arrivals. Solution. Tag numbers are allocated to the events in the same proportions as indicated by the probabilities. Now we can see the problem very clearly in two tables. One is for arrivals and another one is for service time, that is shown here. The random numbers are generated and the linked to the appropriate events. The first 10 random numbers simulating arrival, the second 10 simulating service times. The results are incorporated into an appropriate table on the assumption that the system starts at 0.00 am. Now it is shown in the table. Subdivision 1. Average waiting time per customer is 4.5 by 10 equal to 0.45 minutes. Subdivision 2. Average waiting time or idle time of the services equal to 7.0 by 10 equal to 0.7 minutes. Example. Suppose that the sales of a particular item per day is Poisson with mean phi, then generate 20 days of the sales by Monte Carlo. The cumulative distribution of sales is calculated on the information that sales have Poisson distribution with mean lambda equal phi. The probability for sales is given by P of x equal to r equal to e power minus lambda, lambda power r by r factorial equal to e power minus phi into phi power r divided by r factorial. Now we can see the table or cumulative probability and then tag numbers. After the table, again we have to draw the table for the simulated sales for the next 20 days is with day, random number, sales. Example. A tourist car operator finds that during the past few months the car's use has varied so much that the cost of maintaining the car varied considerably. During the past 200 days, the demand for the car fluctuated as below. Trips per week and then frequency. Now we can see the trips per week as 0, 1, 2, 3, 4, 5 and then frequency is 16, 24, 30, 60, 40 and then 50. Using the random numbers, simulate the demand for a 10-week period. The tag numbers allocated for the various demand level is shown in the table. Using the table, we can clearly write the conclusion for this problem. The simulated demand for the cars for the next 10 weeks period is shown in the table with 3 columns. First column is named as week, second column is named as random number, third column is named as demand. Now we can read the first column. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the second column 82, 95, 18, 96, 20, 84, 56, 11, 52 and then 3. Third column 4, 5, 1, 5, 2, 4, 3, 1, 3, 0. Total demand equal to 28 cars. Average demand equal to 28 by 10 equal to 2.8 cars per week. Conclusion. In this chapter we have covered the following in detail. Axioms and probability, Bayes formula, expectations of random variables, jointly distributed random variables, conditional expectation, bivariate and multivariate Gaussian distribution, some applications, a list model, a random graph, limit theorems, random number generation, simulating continuous random variables, Monte Carlo integration, information theory, measure of uncertainty, Shannon's measure, entropy, joint and conditional entropies, mutual information, Goldberg-Leibler, directed divergence, coding theory and entropy.